Hello students, welcome to my YouTube channel Datasha. Today's lecture we'll be talking about Big M method. In the previous lecture we have talked about the two-phase method. We have done certain examples also. So what is Big M method and what are the steps for the Big M method? So let us consider. The Big M method is a method of solving the linear programming problems. It's a variation of the simplex method, and we generally apply Big M method when there are greater than constraints or equal to constraints. So the Big M refers to a large number associated with the artificial variables, and it is represented by the letter capital M. So capital M is very large. So as in the two-phase method, we designate the cost as -1 for the artificial variables, but in Big M method we designate it as capital M. So what are the drawbacks of this method? If the optimal solution has any artificial variable with non-zero value, then the original problem is infeasible. So other drawbacks that we have is if M is too large, serious numerical difficulties occur. It is inferior than the two-phase method, so it's generally not preferred. So here feasibility is not known until optimality. So the whatever is your last iteration table, you have to calculate it, and at the end only you will be able to understand whether you are achieving a feasible optimal solution as well as the feasible solution or not. Whereas in the case of two-phase method, in the phase 1 we could identify whether the feasible solution exists or not. So the steps remains the same as in the case of two-phase method, but the only difference is there were two phases in the previous method. Here there is only one phase, and that's to the simplex method that we have to apply. So we have to add the artificial variables wherever we have the greater than equal to or the equality constraint, and the value of M is assigned to each of the artificial variables. Then we will solve it by using the simplex method. So again, there are three cases as we have in the two-phase method. If no artificial variable appears in the basis, optimality conditions are satisfied. If there is at least one artificial variable at the zero level, then the optimality condition is satisfied. That means there exists the solution. If at least one of the artificial variable is at a positive level, then there is infeasible solution. So let us consider one example. So we have maximize z minus 2x1 minus x2 subject to the constraints. So we have the equality constraint, greater than equal to constraint, and also the less than equal to constraint, where x1 and x2 are greater than equal to 0. So that's the maximization problem. Now what is the first step? The first step that we have is we have to convert it into the standard form, and in the standard form we'll be applying this adding the slack and the surplus variables we have to deduct. So let us consider maximize z minus 2x1 minus x2 subject to the constraints. As the first one is the equality constraint, so we'll be just adding the artificial variable. So this would be plus a1 equal to 3. So here we'll be just writing it as minus m times a1. The next constraint would be 4x1 plus 3x2. Because this is a greater than equal to, so we'll be subtracting a surplus variable, and accordingly we'll be adding the artificial variable to it with the same cost m minus m, and this is plus 0 times s2. Lastly we have x1 plus 2x2. This is the less than equal to, so less than equal to constraint we always add the slack variable. So this would be equal to 4. So here also, where the non-negativity constraints x1, x2, a1, a2, s1, s2, s3 are all greater than equal to 0. So here when you will be starting with the initial table, the second step that you have is your basic solution. So the basic solution would be achieved when in all these constraints we'll put x1 and x2 equal to 0. So A1 would be equal to 3, A2 would be equal to 6, S3 would be equal to 4. So this is the basic solution where A1, A2 and S3 are the basic variables. These are the basic variables, and the non-basic variables are x1, x2 and s2, and the non-basic variables are x1, x2 and s2. So let us create the first initial iteration table. So the Cj would be the same as we have in the maximization, that is -2, -1. This is big M, this is 0, this is -m, this is again 0. So now with the cost, so -m, 0, so we achieved 3, 6, 4. This was 3, 4, 1, 1, 3, 2. Then the artificial variable that we have was 1, 0, 0. This is 0, 1, 0. And lastly, S3 was also 0, 0, 1. And this one was 0, -1, 0. So as we could see here, Z, if we calculate, this would be -3m, -6m. So that's -9m. Now we'll be calculating the Zj. Zj would be -3m, -4m. So like this would be -7m. This would be -4m. This would be just -m. This would be +m, -m. This is 0. So what is delta J? Delta J again Zj minus Cj. So all the concepts of the simplex method. So -7m, -2. So that's +2. Sorry. So this becomes +2. I'll just erase it and write it properly. So 2 minus 7m we can say. So that's 2 minus 7m. This becomes 1 minus 4m. This becomes 0, m 0, and this is also 0. So now what is the minimum ratio? That means the least negative we are finding out. Then we'll find out the minimum ratio. So the least negative would be this one. So this would be the entering variable, and accordingly we could find out the leaving variable. So 3 divided by 3, that's 6 divided by 4, and 4 divided by 1. So this is 1 point something. So this is 4, sorry. So this would be the leaving variable, as we could observe. So consider the first iteration table. This was the initial iteration table. So in this we'll be entering variable is x1 and the leaving variable is the artificial. This is our pivot element. So coming back to the A1 would leave and x2 would be there. Sorry, x1 is there. So let me just erase this. So this is the pivot element that we have. Now for the pivot element, as we know, the row 1 must be divided by 3. So quickly, x1 is -2. So 3 divided by 3 is 1, 1, 1 by 3, 1 by 3, 0, 0, 0. So this is what we got. A2 remain, S3 remains. So we have to make them 0. So R2 would be R2 minus 4 times of R1, and R3 would be R3 minus row 1. So that's easy to calculate. So let's just quickly find it out. This would be 0 and 0. So 4 minus 1 is 3. This is 2 minus 1 by 3 would be 5 by 3. So this is 0 minus 1 by 3, 0, this is 0, this is 0. So this is what we got. And in the second row we have achieved a 6 minus 4, so that's 2. Then this is 3 minus 4 by 3 is 5 by 3. Then this is 0 minus 4 by 3. This is minus 1, this is 1, and this is 0. So again, quickly calculating the z value, you can this is minus 2, zj would be minus 2, so delta j is 0, and this would be minus 2 by 3 minus 5 by 3 m times m, and this would be minus 2 by 3 plus 4 by 3 times m, and this would be just m, this would be minus m, and that's 0. So zj minus cj, as we could see, the cj is here, so minus 2 by 3 minus 5 by 3 m plus 1, so 1 minus 2 by 3 is nothing but 1 by 3 only, so we'll get here 1 by 3 minus 5 by 3 m. This would be again this is plus m, so this would be 7 by 3 m, this would be m, 0 and 0. Now what's the most negative would be the delta j that we have is here, because this is minus 5 by 3 m. M is a very large quantity, it is a positive quantity, it is there, m is always greater than 0 and it is very large, so we have to keep this thing in mind, and then only we can decide which delta j we have to select. So this would be the entering variable, and what would be the leaving variable? So we could decide x2 would enter, so which variable would leave the basis? This would be 3, 1 upon 1 by 3 is 3, and this is 2 upon minus 4 by 3, so that's because 2 upon 5 by 3, so that's 6 by 5, and 3, that's 9 by 5. So automatically we are getting the lowest one, the minimum ratio that we could calculate. This is the leaving variable, so this becomes our pivot element. So in the last iteration table, the next one, so we'll be having x1 and x2, and this is s3. So quickly, this is minus 2, minus 1, 0, and this is this, and 0, 1, 0. So first of all, for the row 2, we have to just multiply it by 3 by 5, so it becomes 1, and this is 2, 6 by 5. So I'll quickly just write the answers, and this becomes minus 4 by 3, 3 by 5, so it's become minus 4 by 5. Next would be minus 3 by 5, 3 by 5, and 0. Row 1, to make it 0, we have to minus 1 by 3 times row 2. So this would be 3 by 5, and this would be 1 by 3 minus so ultimately we are getting this as minus 3 by 5 as the final answer, and this would be equal to 1 by 5. This we are getting it as minus 1 by 5, and this is 0. And for the last one, row 3, we are getting it as okay, again we have 5 by 3, so row 3 minus 5 by 3 times row 2, so this would be 3 minus 5 by 3 would be 3 minus 2 is 1, and these all 0. So the artificial variable will be getting it 1. Second artificial variable is -1, and these are 1 and 1. So now quickly calculating the z value. As we could see, there are no artificial variables here. So we are getting the feasible solution, the optimal solution here. So z is equal to -6/5, and this is also -6/5. So that would be -12/5. And zj would be, as we could calculate this as -2, this is -1, and delta j is also, we could calculate it as 0, 0. This would be -6/5 and +4/5, so that's -2/5, and so this would be m -2/5. So we could easily see that this is again greater than 0. This would be -2/5 plus 3/5 is 1/5. So that's just 1/5. And second artificial variable, we are getting it as 2/5 minus 3/5 minus 1/5, and this would be m minus 1/5. Again, it would be a positive quantity. So lastly, we are having it as 0, so this would be 0. So as we could see here, all the delta j's are greater than equal to 0. So we are achieving the optimal solution, and the optimal solution would be this -12/5, and also the values that we'll be getting is 3/5 and 6/5. So on the next page, we can write down as all the delta j's are greater than equal to 0. So we got the optimal solution, that is x1 is 3/5, x2 is 6/5, and the z that we are getting, the maximized z, as we are getting it as -12/5. Also, if we put it in the objective function that we have, we could also calculate it from there. So that's again -2x1 and minus of x2. So again, we are achieving the same thing. So this is the Big M method first example, and that is of the maximization type. So in this one, second example, we have minimize the objective function, and this is greater than equal to type. So what we have to do in this, we'll be subtracting the surplus variable, and we'll be adding the artificial variables in the constraint. But the change that you will notice here is that I'll just change the pen. That here the cost associated with the artificial variable is plus m. So always remember this whenever we are doing the problem with the minimization type. Either you convert it into maximization, or if you are doing it with the minimization, then you will be using plus m. So that's the difference between the maximization and the minimization. If you will write it in the maximization type, then it would be maximize z dash, where your z dash is nothing but minus of z. So this would be -40x1 minus 224x2 minus s1 minus 0 times s2 minus m times a1 minus m times a2. Sorry, this is a2. Subject to the constraints, constraint will not change. This would be 20x1 plus 50x2 minus s1. This is the first surplus variable because this is greater than equal to, and plus a1 4800, and this is 80x1 plus 50x2. Again, it's a greater than equal to, so we'll be writing minus the surplus variable plus the artificial variable a2 equal to 7200, where x1, x2, s1, s2, a1, a2 are all greater than equal to 0. And similarly, we can plot the first initial table using, I have done it with the maximization type. So you could see here the CJs and everything remains same. Now the difference between the last example and this example is when we are finding the basic solution. When you find the basic solution, you put x1 x2 equal to 0, and so what we are getting, a1 as 4800 and a2 as 7200. so these two are your basic variables. So that's in the basis. So rest everything is the non-basic variables that we have. So here also you will notice these are a1 and a2. So in the previous example that we did, we have the basic variable as the S3 that we have, and that was related to the less than equal to the slack variable. So that was also in the basic variable basis. So that's why it is considered in the basic variable. So now in this the steps remains the same. You have to calculate your z, the zj, delta j, and you will be calculating the most negative. This is the most negative that we have here, because that's minus 100 plus 24m. So obviously this is the most negative, and when we have to find the minimum ratio, as we could easily identify, this is the minimum ratio. So this would be the leaving variable, and this is the entering variable, and this becomes our pivot element. So we have to divide the whole row by 50 so that we can a1 can leave and x2 can enter. So when a1 will leave and x2 will enter, so this is what we are having. So the elementary row operation would be row 1 would be divided by 50, and row 2 would be r2 minus 50 times row 1. So ultimately we will be getting this new iteration table. So again here we will be calculating the same steps, delta j, the most negative. Now the most negative would be, here you will see this is 152 divided by 5 minus 60m. So m is a large quantity that is multiplied by minus 60. So obviously it is the most negative. So out of all these m values, this is the most negative. So this would be the entering variable. x1 will enter, and obviously this is the leaving variable that we have. So this is our pivot element. So in this pivot element, that means a2 is leaving and x1 is entering. So we'll be dividing the whole equation by, here you will notice that r2 will be divided by, this is the pivot element, so divided by 60, and r1 would be r1 minus 2 by 5 times r2. So we are getting this. Now in this, when we solve the write the next iteration table, you will notice that still we are getting a delta j as negative. Rest everything is positive. That means this would be entering. Now this is a surplus variable. So it's not necessary that if you have in the basis variable, basic variables, we have entered x1 and x2. So your delta j must be greater than 0. It could be less than 0. So now here S1 is the entering variable, and the leaving variable that we have is x1. So it is leaving, and this becomes our pivot element. So finally, the last iteration table that we have achieved, where all the delta j's are greater than equal to 0. So that means we are having x2 and s1 in the basis, and our z that we have got is 3, 4, 5, 6. So what would be the solution? The solution here that we'll be getting would be x1 is 0, x2 is minus 144, and s1 that is 2400. So in the maximization, because this is a maximization problem, so you are getting maximized z as 3, 4, 5, 6. So this is z dash, right? So minimum z would be minus 3, 4, 5, 6. So this would be your final answer. So this is how we can solve the question using the big M method. So in the next lecture also we'll be doing one more example. So we'll meet in the next lecture.